Hello and welcome back. So in this part of the lecture I want to talk about how the alveoli are going to exchange carbon dioxide and oxygen, and then how the blood will transport these gases to their respective places. So the alveoli are the only sites of gas exchange between the atmosphere and the bloodstream. So these are basically tiny little sacs that are clustered at the ends of these structures called the alveolar ducts. Those are the smallest ducts that terminate into the alveoli. And they start out as big bronchial, bronchi, right and left bronchi, and they get smaller and smaller until they form bronchioles, and then finally the alveolar duct. There are three cells that are found in the alveolus that do the job of to help the alveoli do gas exchange. So type 1 alveolar cells are literally the simple squamous epithelial cells that make up the wall of the alveolus. And they're thin for gas exchange to occur. Type 2 alveolar cells are going to secrete alveolar fluid or surfactant. This is a fluid that when you exhale and the alveoli decrease in size, this fluid doesn't allow the walls of the alveoli to stick together, thus collapsing the alveolus altogether. The alveolar macrophages are also an important part of the alveoli, and they're going to remove debris from the space, the alveolar space. They can also remove microorganisms as well. So the respiratory membrane is going to be a really thin membrane, and it consists of the epithelial cells of the alveolus, which are simple squamous epithelial cells. It also includes the endothelial cells of the capillary, the walls of the capillary, which are also simple squamous. And then there are two fused basement membranes, and so that basically is what the respiratory membrane is made of. Gas exchange is going to occur across this respiratory membrane, and let me go over here and go over a little bit of the anatomy there, and then I'll show you what the respiratory membrane looks like. So if you look at this box right here, it kind of shows you how how we have the bronchioles. They're branching down into the alveolar ducts, and then the alveolar ducts are leading to the alveolar sacs, and then to the individual alveoli. So you can see that the alveolar ducts are the last little part that then eventually branches into the little sacs. So if we take a look at an alveolus, so this would be how this thing is arranged. There are three types of cells there. We have the type 1, and in different textbooks will have different names. In this particular graphic they're using pneumocyte, but this type 1 pneumocyte. So there's various names that you can use for this, but this is the simple squamous epithelial cell that is making up the wall of the alveolus. We have alveolar macrophages, and these are going to be gobbling up microorganisms and debris. And then we have type 2 cells, which are going to be producing that fluid called surfactant that lubricates these so they don't collapse in and stick to themselves when air is exhaled out of them. We can also see the arrangement of capillaries along the walls of the alveolus. So you can see capillaries that are right there. So this is the respiratory membrane, and it's made up of the simple squamous epithelial cell of the capillary. It's made up of the simple squamous epithelial cell, that's cells that are making up the wall of the alveolus, and then it's made up of the two fused basement membranes, which is the middle layer in the sandwich there. Okay, so gases are going to diffuse this way, or gases are going to diffuse this way. Typically, oxygen is going to move this way from the alveolar space to the red blood cells, and then carbon dioxide is going to move this way from the tissues to the alveolar space to be exhaled out. All right, let's talk about the respiratory membrane and how diffusion works. So when we take a look at gases diffuse from areas of high pressure to areas of low pressure. So it follows the normal, physical process of diffusion. And when you look at a mixture of gases, so if I were to have a bottle and have gases inside of those, so in a mixture of gases, each gas is going to account for a portion of the total pressure. So inside this chamber here that's sealed off, I have a little cap over it, there is a pressure inside called the total pressure. And that total pressure is a mixture of all the gases, of all the partial pressures that each gas exerts on the total pressure. So, so the amount of pressure that each gas exerts is equal to its partial pressure. So in this chamber here, I could have a partial pressure of oxygen, so it's basically represented by a lowercase p and then an O2, and then you might have partial pressure of carbon dioxide, and there might be partial pressures of other gases like water vapor. Okay, so all of these partial pressures are going to equal the total pressure. So each gas will exert a little bit of that total pressure, and that's going to equal to its partial pressure. When the partial pressure of oxygen is higher in the alveolar air than it is in the capillary blood, then oxygen is going to move from the alveolar air to the blood. If the partial pressure of carbon dioxide is greater in the blood than it is in the alveolar air, then carbon dioxide will diffuse out of the blood and into the alveolus. So essentially the gases are moving from wherever they're the highest partial pressure to the areas of where they're the lowest partial pressure. So we're just following physical properties of the physics of how gases are moving. So a lot of things will basically favor increased diffusion in your lungs. So great surface area, that's basically going to help to favor diffusion. Where there's a short distance, that is good for diffusion. If you had a thick, chunky lung, the gases wouldn't be able to diffuse through those thick tissues. So the solubility of gases, having a warm, moist environment inside the alveolus is good for gas exchange. Gases don't typically exchange very well through these membranes without it being moist. And then where the gases have a really, really steep partial pressure gradient, this helps to aid in the diffusion of gases. If the gases aren't very different on either side of the membrane, then they're not likely to diffuse that much. But when you have a great difference in the pressures on either side of the respiratory membrane, that really leads to these gases diffusing through. So gases are transported in association with molecules in the blood, or they can be dissolved in the plasma of the blood. So let's talk about oxygen transport first, and then we'll do carbon dioxide. So over 98% of the oxygen in your blood is going to be carried by hemoglobin molecules. When the oxygen joins with the hemoglobin molecule, it forms oxyhemoglobin. So that's the name we use for hemoglobin that's joined with oxygen. Oxyhemoglobin is unstable in areas where concentration of oxygen is low. Okay, so that's good. So where you need oxygen, where oxygen is low, then the oxygen that's bound to the hemoglobin molecule is very unstable, so it can be released, so it can go to where those tissues that need the oxygen. Okay, so being unstable means that it gives up the oxygen molecules in the areas where they're needed. So more oxygen is released as the blood concentration of carbon dioxide increases. Okay, so you can imagine that a place in your body where there's high carbon dioxide levels would be places like your muscle tissue when you're doing physical exercise. Now your muscle tissue, when it's doing physical exercise, needs lots of oxygen. Okay, so you want oxygen to be released from the oxyhemoglobin molecule so it can go to the tissues. So where you have high carbon dioxide levels, that makes the oxyhemoglobin molecule unstable, thus releasing the oxygen. Places where you have blood becoming more acidic are places like exercising muscles. Okay, so they do have some acidity there. So where you have acidity, it makes the oxyhemoglobin molecule more unstable, thus oxygen will be released. And places where the blood temperature increases is going to make the oxyhemoglobin molecules unstable as well, and thus it will release oxygen. and you would expect your muscle tissue when it's exercising to be warmer because of the friction of the muscle contractions. So anywhere where you have high carbon dioxide, high acidity, and high temperatures, it's going to make the hemoglobin molecule release oxygen to those tissues. So if you have a deficiency in oxygen-reaching tissues, that particular condition is called hypoxia. Okay, and there's a wide variety of causes that can cause hypoxia, like a lack of blood, you've lost blood, you have anemia, so a lack of hemoglobin molecules. All of those things can cause hypoxia. A block of the flow of blood to a tissue can also cause hypoxia. All right, let's look at how those partial pressures are working. And let me set this little diagram up for you. It's a really simple diagram. So this is basically an alveolus. And here is the blood coming to the lungs. Here's the blood leaving the lungs. So if we look at blood coming to the lungs, the partial pressure of oxygen and carbon dioxide, the partial pressure of oxygen is 40 millimeters of mercury. The partial pressure of carbon dioxide is 46. So if we look at inside of the alveolus, the partial pressure of oxygen is 100, partial pressure of carbon dioxide is 40. So what we have is blood coming to the lungs. We're going to have a situation where, since you have a high partial pressure of oxygen, the oxygen is going to go to the blood cells. And where we have a low partial pressure of carbon dioxide, here we have a high partial pressure of carbon dioxide, the carbon dioxide is going to go this way and be exhaled out of the lungs. Notice that the partial pressure of water is 47, but the air that you're breathing in, it only has 6. So we do warm and moisten the air, and that aids in gas exchange at the respiratory membrane. So blood leaving the lungs, is going to have a partial pressure of oxygen of 95 millimeters of mercury. So it has increased a significant amount from what it looked like when it came in. And you can see that carbon dioxide is a partial pressure of 40, so we were able to drop off some carbon dioxide in the lungs. Okay, so this blood will now go to arterial circulation and circulate to all the parts of the body to deliver that oxygen and to pick up carbon dioxide. And so this is showing you that the hemoglobin molecules coming to in the capillaries coming by the alveolus, they're picking up oxygen. So you can see oxygen is diffused into those molecules. So now we have oxyhemoglobin. So the partial pressure of oxygen leaving the lungs is 95 millimeters of mercury. But when we get to the tissues, tissue partial pressure oxygen is 40 millimeters of mercury. So you could assume that the oxygen is going to move from an area of high partial pressure to an area of low partial pressure to the tissues of the body. Okay, so that's how the gases will diffuse in your capillaries when the arteries are carrying nice oxygenated blood to the capillaries. So at the end of the capillary bed, the partial pressure of oxygen has lowered, so we stop dropping oxygen off to the tissues. That blood flow will go to the lungs to pick up oxygen so that partial pressure can be greater again. Okay, so what I call these are hemoglobin saturation curves. What you have in the x-axis is the partial pressure of oxygen in millimeters of mercury. It goes all the way from 0 partial pressure to 100 millimeters of mercury partial pressure. So if we take a look at the percent saturation of hemoglobin, that's going to be graphed on the y-axis. So we have 0% of the hemoglobin molecule is saturated, up to 100% of the hemoglobin molecule is saturated. So if we look at deoxygenated blood in the skeletal muscle tissue, we can see that the partial pressure of oxygen is 20 millimeters of mercury. And if you notice, at 20 millimeters of mercury partial pressure of oxygen, somewhere in the order of 75% of the hemoglobin is saturated with oxygen. Okay, so at respiring tissues, you have a very low partial pressure of oxygen, and that's the saturation you get of the hemoglobin molecule. At higher partial pressures of oxygen, say at 40 millimeters mercury partial pressure, you get somewhere in the order, pardon me, I messed that up. Let me redo that, that other one. That's not what I meant. So at low partial pressures of oxygen, you have low saturation of the hemoglobin molecule. So you can see that it's only about 35% saturated at a low partial pressure. So at a higher partial pressure of, say, 40 millimeters of mercury, we're going to have somewhere in the order of 75% of the hemoglobin molecule will be saturated. But at really, really high partial pressures of oxygen, we can almost totally saturate those hemoglobin molecules almost to 100%. Okay, so at very low partial pressures of oxygen, very low percents of the hemoglobin molecule are saturated. At very high partial pressures of oxygen, we have almost all of the hemoglobin molecule is saturated with oxygen. I sometimes like to think of the hemoglobin molecule as being like a roller coaster. You know, a roller coaster only has a certain number of seats. So so you can fill very few of the seats, or you can fill almost all of the seats. But there are seats that allow oxygen to sit on or to sit in, and those seats can be completely full, or those seats can, or the roller coaster can be, relatively empty. All right. Now, this is the normal curve right here, normal saturation curve that hemoglobin does. You can see that at low partial pressures, very few of the seats are filled with oxygen. At really high partial pressures, a lot of the seats are filled up. Almost 95% of the seats are filled up at a very high partial pressure. And that's the normal curve that hemoglobin is saturated at. So that little S curve there is the normal, the black curve is the normal curve. But if you notice, the curve can shift to the right or it shifts to the left. And what this is this. So at low pHs, that is when you have a muscle tissue that's working really hard and is creating acids that it's releasing into the bloodstream, at low pHs, it's reducing the pH, oxygen has less affinity for the hemoglobin molecule. So another way of thinking about that is that you can see that at this partial pressure, the hemoglobin molecule has greater affinity, more oxygen sitting on the hemoglobin molecule than at this place right here at a low blood pH. So oxygen's being forced off of the hemoglobin molecule at low pHs, and that's why you see this curve looking like this. Okay, and it makes sense that it does that. You want oxygen to have less affinity, less stick-to-itness to the hemoglobin molecule if the tissues really need that oxygen. Okay, so at a high pH, oxygen has a greater affinity, or it sticks to the hemoglobin molecule a little bit more, or a little bit stronger. Thus, the curve shifts up here to the left. Okay. Same thing at a high carbon dioxide level. Carbon dioxide will actually sit on the roller coaster seats and thus not allow oxygen space to sit on the roller coaster. So it competes with oxygen for the seats on the hemoglobin molecule. So again, normal curve is black. At a high pH, at a high partial pressure carbon dioxide, it forces oxygen off of the hemoglobin molecule to the tissues that need that. At a low carbon dioxide level, though, the hemoglobin molecule has greater affinity, or oxygen stays on it more easily. So that's why you see the curve to the left as opposed to the curve to the right. So at high temperatures, again, the hemoglobin molecule will release oxygen, or oxygen will have less affinity for it. It'll be unstable and have less affinity for it. Thus, it's going to release the oxygen to the body tissues. At really, really low body temperatures, you're going to have the oxygen not being released off the hemoglobin molecule. So hemoglobin molecule will have greater affinity for oxygen at low body temperatures. Now this is kind of an interesting curve here. Here we have fetal and maternal curves, saturation curves. So the fetal curve, you can see that the fetal hemoglobin molecule has greater affinity to oxygen. And in order for a fetus to survive, it has to literally pull oxygen off of mom's blood cells. So in order to do that, its hemoglobin molecules have greater affinity for oxygen, so it basically is going to pull oxygen off mom's blood blood cells or hemoglobin molecules and pull it towards itself. So it has a greater affinity for oxygen than mom's own blood. If you look at the molecules of myoglobin inside of muscle tissue, it has a super great affinity for oxygen molecules, trying to draw it into the muscle tissue. And creatures that live at high altitudes are going to have different saturation curves. They're going to have saturation curves where, at really low partial pressures, they're able to pull a lot of that oxygen out of the atmosphere and put it onto their blood cells. Okay, compared to the normal, just a normal saturation curve for a person that lives at say sea level. Okay, so there are creatures that are adapted to living at high altitudes. Their oxygen has a greater affinity. Their hemoglobin molecule has a greater affinity for oxygen. All right, let's talk about how carbon dioxide is transported. So carbon dioxide can be transported in the blood plasma just as a gas. It can be transported as bicarbonate ions, and I'll show you how that works in a minute. Or it can join with the hemoglobin molecule to form carbaminohemoglobin. So it literally can sit in the seats of the roller coaster, hemoglobin being the roller coaster. It can sit on the hemoglobin molecule. Most carbon dioxide, though, is transported in the form of bicarbonate. So when carbon dioxide reacts with water in the plasma of your blood, we do form this substance called carbonic acid. Carbonic acid is slow to form, but much of the carbon dioxide that enters into red blood cells is going to be converted by these enzymes this enzyme called carbonic anhydrase to form this carbonic acid. Okay, and when the carbon dioxide enters into a blood cell, this reaction is sped up as opposed to in the plasma of the blood because there's more enzymes inside of the red blood cell. So this carbonic acid is going to dissociate, and it dissociates into bicarbonate ions and hydrogen ions. And I'll show you what those things do in 1 minute. So another way that carbon dioxide can be transported is forming carbaminohemoglobin. So it joins with the hemoglobin molecule, and this carbon dioxide will be released once the blood gets to the respiratory membrane in the lung, and it'll be basically taken outside of the body and exhaled. Okay, so let's take a look at a few pictures of these processes. So here you can see that carbon dioxide is dissolved in the plasma of the blood, and if we looked at the partial pressure carbon dioxide, it's going to be about 40 millimeters of mercury in this particular graphic here. So if this is a capillary and these are the tissues of the body, you can see that the tissue partial pressure of carbon dioxide, is 45 millimeters of mercury. So you can see this is greater than this figure down here. So because the partial pressure is greater, then those gases are going to diffuse from the tissues of the body into the capillary bloodstream. Now, once those tissues have released their carbon dioxide to the bloodstream, some things are going to happen to it. You can form carbaminohemoglobin, that is, the hemoglobin molecule will join with the carbon dioxide and form carbaminohemoglobin. That carbon dioxide can join with water and form carbonic acid, which will then dissociate into bicarbonate ions and hydrogen ions. So that's a possibility of what could actually happen to it. Okay, so here is is what we call the carbonic acid bicarbonate buffering system. So the carbon dioxide that we bring in can join with water to form carbonic acid. That carbonic acid can dissociate into hydrogen ions and bicarbonate ions. And that bicarbonate ion, as it builds up and builds up and builds up, we don't really want to keep that into the blood cell because that can disrupt the osmotic balance. If we kept it in there, then water would basically leak into your blood cells and cause the blood cell to swell up and perhaps even burst if it's swelled up enough. So to get rid of that large molecule, we have this thing called the chloride shift. So we take and we and we shift out bicarbonate and put it into the plasma of the blood. And to make sure that nothing electrically changes, so we're getting rid of a negative and bringing a negative in, we basically bring chloride ions into the blood cell. Okay, so that basically is a safety mechanism. It ensures that osmotic balance stays the same inside the red blood cell so that it doesn't swell up with water. To maintain electrical neutrality, we basically bring in chloride ions and we take out the bicarbonate ions. They're both negative, so we're not changing the charge. Now these hydrogen ions can actually combine with the hemoglobin molecule, and that's what this little part down here means. Okay, now this picture puts it all together, and it's a pretty sophisticated picture. So let's take one little step at a time. So let's look at the top one. So what this is showing you is the exchange of carbon dioxide and oxygen in the pulmonary capillaries. So these are basically so this is the respiratory membrane right here, and this is how the gases are moving. So we are going to take oxygen, and because the partial pressure is great here, but it's very little in the red blood cell, oxygen is going to diffuse into the red blood cell. When oxygen diffuses in, it's going to displace that hydrogen ion right there. Okay, so we had hydrogen ions that were joined to the hemoglobin molecule. So when we displace that hydrogen ion, that's going to take bicarbonate that's diffusing into the blood cell. Those hydrogen ions and bicarbonate are going to join together to form carbonic acid. That carbonic acid is going to dissociate into water and carbon dioxide. Carbon dioxide is going to be released so that it can travel out and be exhaled out of the body. Now, because we bring bicarbonate in, if you take a look right here, because we bring carbonate in, we shift chloride out to maintain electrical charge. We don't change electrical charge. Okay, and notice that there could be some carbonaminohemoglobin that releases carbon dioxide. That carbon dioxide would also be exchanged out. Okay, so that's pretty sophisticated. You may need to take your textbook and read a little bit on that, and just to get a sense of what's going on there. Now let's look what happens though when we get down to the walls of the capillaries in systemic circulation. Notice that kind of like the opposite is occurring. So we're going to take and upload carbon dioxide into the capillary. So carbon dioxide is going to come across the wall of that capillary. It's going to go into, if we take a look, it's going to go into the blood cell, combine with water to form carbonic acid. Of course, we're going to form bicarbonate and hydrogen ions. The bicarbonate is going to diffuse out of the cell into the plasma, shifting chloride in to maintain electrical charge. We're going to have also those hydrogen ions right there. Hydrogen ions are going to join with the hemoglobin molecule, displace oxygen, thus oxygen is going to be released to the tissues, and will form the hemoglobin molecule we'll have the hemoglobin molecule attached to hydrogen there. So another thing that occurs as carbon dioxide comes in is it can join with the hemoglobin molecule to form carbonaminohemoglobin, and it thus displaces oxygen so it can be released to the tissues as well. Okay, so that's pretty sophisticated. You might want to go back and just kind of re-listen to the lecture, or make sure you read in your textbook this particular mechanism. Well, a lot occurs with age. As age, we basically will reduce our vital capacity, we'll reduce our blood oxygen levels, the alveolar macrophage activity will decrease, and so will the ciliary action of the respiratory epithelia. So a lot of things begin to decrease as we age. The elasticity gets less and less in your alveoli as well. The more you can exercise, keep a good diet, and not smoke, the longer lasting your respiratory system will be. So People who are elderly are more susceptible to pneumonia because of the reduction in the immune system. People that are older are also going to have more bronchitis because the ciliary action is going to be diminished. They also have less spring in their alveoli because the elastic tissue is damaged or destroyed, and that causes emphysema. And then, of course, there's a whole host of other kinds of issues that occur in older people. I just wanted to show you there that as you age, your respiratory performance is going to diminish over time. The rate at which it diminishes is going to be up to you. So if you don't smoke, then its rate of diminishment is going to be much less. If you do smoke but you stop early, then the rate of diminishment will be less. So anytime you stop smoking, your rate of diminishment will be less and less. But if you exercise, you can actually, cause it to last a lot longer. So it's all in your hands as to what's going to happen to your respiratory system. Never, ever, ever learn a system without putting it into context. So the respiratory system is going to be basically involved in all the different systems of the body, and you should always put that into context and understand how all the systems of the body are integrated into all the other systems. Okay, well, that does it for the respiratory system. Next time we'll be diving into the digestive system. So until then, I will see you next time.